In this video, we're going to look at how to do a chi-square test, chi-square goodness of fit test using the TI graphing calculator. And I'm going to do about 3 different examples because depending on the given information, depending on how things are given, you handle the test a little bit differently in the graphing calculator. So I like to make up stories. A story here I'm going to use is when I'm playing board games, I have a favorite set of dice. Okay, it has been stated that I like those dice because it seems that when one die is rolled, it comes up 6 more than it should. So recently I rolled one of the dice 600 times and I logged the results of each of the rolls. And the results are shown in the table. So you can see that of the 600 rolls, I got a 1 92 times, I got a 4 94 times, I got a 6 111 times, and so on. To test whether the dice is fair, the die is fair, I'm going to conduct a chi-square goodness of fit test to determine whether we concluded that the proportions are not all equal to each other. So remember that if I roll the dice 600 times and the probability is 1 out of 6 of getting a 1, a 2, a 3, a 4, a 5, or 6, I would expect to get each of those values, 1, 2, 3, 4, 5, 6, approximately 100 times. Now, do these numbers look approximately 100 times each? Fairly close, but let's just go ahead and do that test. So the first thing I'm going to do is go to Stat, Edit, and List. In a chi-square test of homogeneity or in a chi-square test of independence, the data is put into a matrix. But for the goodness of fit test, we put the data into a list. And I like to put, something. I guess I was going to say I like to put the observed in L1. I'm trying to get myself into the habit of putting my observed values into L1. So let's just go ahead and do that. My observed values are 92, 107, 91, 94, 105, and 111. Those are the observed values. Let's type in that number correctly. So those are my observed values. And in L2, I'm going to put in my expected counts. So if I roll the die, I'm not going to put in the probability for the calculator. I'm going to put in the expected counts. So if I roll the die 600 times and the probability is 1 out of 6 to get a 1, 2, 3, 4, 5, 6, I would have expected to get each number approximately 100 times. So those are my expected values. Okay. So now if I go to Stat and over to Tests, and I go down this list looking for the chi-square test, notice that first I'm going to come to option C, which is a chi-square test. That would be for the test of homogeneity or the test for independence. We're doing a chi-square goodness of fit test, therefore we're going to use option D. And in the chi-square goodness of fit test, I told you I'm trying to get in the habit. The default for the calculator is that the observed is L1 and the expected is L2. So I'm trying to get in that habit, and I'll present it to you this way as well. Okay, observed is L1, expected is L2. Degrees of freedom, remember that degrees of freedom is n minus 1 or k minus 1. In this case, we've got 1, 2, 3, 4, 5, 6 categories. Therefore, our degrees of freedom is k minus 1, 6 minus 1, or 5. Okay. And now we're going to go to calculate. We have a chi-squared value of 3.76 and a p-value of 0.584. So since my p-value is greater than probably 0.1 or 0.05 for my alpha, we cannot reject the null hypothesis. We could not conclude that, in fact, that the dice are giving me numbers disproportionately towards 6s or something else. So it does appear to be a fair die. Okay, so that's one example in the calculator. The next example I have is instead of rolling 1 die, I'm rolling 2 dice. Now remember that when you roll 2 dice, you're looking at the sum. So if I roll 2 dice, what's the probability of getting 6? To get a 6, I could get a 1 and a 5, a 2 and a 4, a 3 and a 3, a 4 and a 2, or a 5 and a 1. So remember from probabilities, you are more likely to roll 2 dice and get a sum of 6 than you are to roll 2 dice and get a sum of 3. So in this case, the probabilities are not all the same. So in the graphing calculator, I'm going to come back here and I'm going to make my L1 my observed values again. In these 600 rolls of the 2 dice, we got a sum of 2 20 times, a sum of 3 28 times, a sum of 4 51 times, and so on down the list. So I'm going to enter those observed values, okay, each time. Now, in the calculator, I'm going to have the calculator do a little bit of work for me, okay? The probability of rolling a die and getting a 2, if you recall, is 1 out of 36, 2 out of 36, and so on. Now, I'm a little bit lazy, so what I'm going to choose to do is just say the probabilities were 1 out of 36, 2 out of 36, 3, 4, 5, 6 out of 36, and then 5, 4, 3, 2, and 1 out of 36. And the reason I do that is that now when I put my cursor back up onto the L2, what I can do is press enter, and notice my cursor is here now, second L2 divided by 36. And there's all of my 1 over 36 and 2 out of 36 and 3 out of 36 and so on. But now that's the probability. What the calculator is looking for that list to be is not the probability, but the expected number. So I'm going to do one more multiplication here. I'm going to do L2 is now going to equal the current L2 times 600, because I'm going to roll the dice 600 times. So if I do 1 out of 36 times 600, 16.667 is how many times out of the 600 rolls I would expect the dice to come up as a 1, and so on. So that's the number of rolls, not the probability. Now, if I go back to stat, tests, this time to get to the bottom of the list, I'm simply going to scroll up. And I'm at the bottom of the list, I'm going to select option D. I'm also going to remember the chi-square goodness of fit test is option D. I press enter. Yes, my observed is in L1. My expected is in L2. My degrees of freedom, be careful, I don't have 12 here. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 categories. So degrees of freedom is 11 minus 1, or 10. Calculate that. I have a chi-square value of 8.929. P-value is 0.539. Therefore, I cannot conclude that the dice are unfair. Okay, my null hypothesis was probably something like there is no relationship, right, between the numbers, or that the proportions, I like this, the proportions are as expected. It's expected that the dice will come up at 2 approximately 1 out of 36 times, to 3, 2 out of 36 times, and so on. So my null hypothesis is that the proportions are as expected. Alternate would be the proportions are not as expected. And so therefore, since we cannot reject a null hypothesis, we cannot conclude the proportions are not as expected, and we cannot conclude that the dice are unfair. And so we're going to play the game as if they are fair. Okay. One more example to look at here. In a particular city, the Chamber of Commerce has been debating whether it's reasonable to conclude that the post-secondary educational attainment of its residents has changed in the last several years. The table below indicates the post-secondary educational attainment in 2014 and in 2018 based on a sample of 1,000 residents in each year. Test at a 95% confidence level whether the chamber can conclude that the attainment has changed from 2014 to 2018. So what I'm wanting to do, what I did originally, is I said, okay, my observed values in 2018, actually let's clear these lists. Enter, clear, enter. Go up onto the L2, hit enter, clear, enter, the lists are clear. My observed values are the values, let's try this again, in 2018. So this is going to seem a little backward, but observed is 2018. And expected is 2014, because I'm wondering if things have changed since 2014. So my null hypothesis is equality, that nothing has changed, that in 2018 the data is the same as it was in 14. Okay, so I'm expecting no change. That's my null hypothesis. That's why I put the 2014 in expected. 2018 is what I'm now observing in 2018. I wonder if that's different. So I just put in those proportions. I put in those percentages. Stat, tests. This time to get to the chi-square test, remember it was option D? We can simply select alpha D and we go to the chi-square test. Observed, we put in L1. Expected, we put in L2. Degrees of freedom, now notice we only have 1, 2, 3, 4 categories. That's 3 degrees of freedom. And let's see what happens when we calculate. The calculator is not happy. The reason that the calculator is not happy here is the calculator is expecting that these values are observations, expected numbers, how many. This is why I said a sample of 1,000 residents. So these would all need to be multiplied by 10. So 478 of the 1,000 residents, 73, 269, and 180 of the residents who were surveyed gave us those indications. Remember, for L2, I could have done this for L1 as well. I could press enter, second L2 times 10, and I do all 4 multiplications at the same time. So now if I go back to stat test option D, observed, expected, still 3 degrees of freedom, the calculator will calculate this much more easily. So we have a chi-square value of 6.135 with a p-value of 0.105. And so again, we cannot reject our null hypothesis. We cannot, in this situation, conclude that there's been a change in the distribution of post-secondary degrees earned from 2014 to 2018. Clearly, the samples are different. The sample in 18 is different than the sample in 14, but they're not different enough to conclude that for the entire population that there's a difference. Okay, so there's a quick look at chi-square goodness of fit test using the graphing calculator.